Recording has started.
So for both of these, we're asked to find the gallons or liters, the capacity. But of course, we're given the links for them, which means we have to calculate volume. Remember, we discussed yesterday, volume is found from lengths, combining lengths and capacities at standard containers. So we have to do that conversion. So our first one here is a standard measurement in inches. So I'm going to do the area of the base there first, which is just that bottom piece, which is 38 inches by 22 inches, which is 836 inches squared. So the volume is that 836 square inches times that 8 inches of height. Give us 6,688 cubic inches of volume. Now we want that in gallons. 6,688 cubic inches over 1. We're going to put cubic inches on bottom so they cancel out, going into gallons. The conversion we have is 1 gallon is approximately 231 cubic inches. So the cubic inches cancel out. This will be the 6688 divided by 231, giving us 28.95 gallons. So just under 29 gallons for that tank. For number 2 here, we'll find the area of that base. Again, the base will be that bottom side, the 96 by 52. (4,992 square centimeters). So then the volume, 4,992 square centimeters times 21 centimeters of height, right there, gives 104,832 cubic centimeters. Now, realistically, as we've seen, we would not leave that as 104,000 cubic centimeters. It's too large of a number. We could convert it to cubic meters. Remember, meters is 2 spots to the left on the chart. Every spot for cubic would be 3 decimal places. So that would be 0.1 cubic meter, or 1/10 of a cubic meter. But for our purposes here, we're converting it to liters. So we want to leave it as centimeters cubed right now, because 104,832 cubic centimeters, if I'm converting that to milliliters, 1 cubic centimeter equals 1 milliliter. That's 104,832 milliliters. There's no conversion to make. A cubic centimeter and a milliliter are the same thing. You hear, if you look at motorcycle engine ratings and even some medications, they give it in cc's. A cc is a cubic centimeter. So that is a milliliter. Well, now that we have it as milliliters, we can convert it to liters, because on the chart, from milliliters to liters is 3 spots to the left. So let's move our decimal point 3 spots to the left. That's 104.832 liters in that tank. So it's just under a 105 liter tank. Now, a side question here, it wasn't part of the problem, but I'm going to throw it out there anyway. Which is bigger? Well, I have to convert one way or another. Either I have to take the 28.95, turn it into liters, or the 104.832 and turn it into gallons. Let's do the gallons to liters. Let's take the 28.95 gallons, put it over 1. 1 gallon is 3.785 liters. So the gallons are going to cancel out. We're going to take 28.95, 3.785, 109.58 liters is what we're at. So that 28.95 gallon tank is just slightly larger than the 104.83 liters in the other tank. So those two problems illustrated the difference between volume and capacity that we talked about yesterday, where volume is derived from those length measurements. Capacity is those standard size containers. Remember, we said the only way to measure capacity is to actually either fill it up with something and see how much it takes, or to put it into one of those containers and see how many containers it fills, where the volume can just be measured out and calculated. Well, today we're going to start out with something similar. We're going to talk about the difference between weight and mass. Now, on Earth, which is where hopefully all of us live most of the time, we tend to jump kind of recklessly back and forth between mass and weight, even though they are a different thing. Weight is a measurement of the force of gravity on an object. Mass is a measurement of the amount of matter. In an object. Now, like I said, on Earth, the two tend to be, we tend to jump back and forth pretty recklessly between them, but they are closely related. The more mass something has, the more it weighs, and gravity is really the factor that connects the two. Gravity is pretty consistent. Well, let's look at how they're measured, really, to point out the difference between them. To understand how weight is measured, we have to look at a spring, and what a precision spring, or a good spring, and how it behaves. If I have a spring that is at rest, so that just means it's sitting there with no force on it, and it stretches to there. We're going to call that the 0 point. That's zero location. If I stretch that spring, to a certain distance. So now I've gone a certain distance away from that 0 point. I'm just going to label that X for now. It takes a certain amount of force to stretch it that far. If I go and I stretch it so that it is now twice as far away from that initial resting point, 2x, that takes twice as much force. So if the force here, if it takes F amount of force, this takes 2F force to stretch it twice as far. Of course, and that'll continue up to a certain limit. At a certain point, it'll be too much force for the spring, and it'll permanently bend the spring or deform the spring. But up until that point, as long as we release it back before we get to that point, the length that spring stretches is very, very precisely related to the amount of force that is put on it. So because of that, we can use that to measure other forces. The way we do that is we take that spring and we put it into a casing, and on that casing we mark distances, and we put an indicator where that spring is at rest. And that marking, the reason it's called a scale, is the markings that are on this edge over here are marked out to scale. Now, when we hang our object on there that we're trying to measure, to weigh, it's going to stretch that down. That indicator is going to move as the whole thing drops down. And where that indicator is at tells us how far the spring is stretched, which tells us how much force is on that spring. So that's how we measure weight, is by putting that object on a spring and seeing how far the spring stretches as gravity pulls down on the object. Mass is measured using a balance. A balance is basically a really, really precise seesaw or teeter-totter, however you want to think about it. We place the object that we're trying to measure on one end, and then on the other end we place known masses. And whenever it balances, whatever the mass is of this object is the mass of what we are trying to measure. So whatever known mass balances it is its mass. Now you might look at that and say, well, what's the difference? And really, like I said, on Earth, gravity is constant as we move around the planet pretty much. There's about an 8% difference from the North Pole to the equator. So that means a 200-pound person would weigh 10 or 15 pounds less at the equator than they would at the North Pole. But gravity, like I said, is still relatively constant, close enough to the point where we kind of do jump interchangeably between weight and mass. The difference is mass does not depend on gravity. But what do I mean by that? Well, if we go to the moon, where gravity is about 1/6 what it is on Earth, on our scale, there's going to be 1/6 of the force because there's 1/6 of the gravity. So the weight is going to be 1/6 of what it is on Earth. On the balance, well, the amount gravity pulls on this goes down, but the amount it pulls on the known mass goes down. It's still the exact same amount of mass that's going to balance it. So mass does not change when we have more or less gravity. Mass is a constant. It does not depend on the gravitational field we're in. In the standard system, we tend to focus on weight. So let's look at our standard mass unit first. The unit for mass in the standard system is called a slug. A slug is 32 pounds. It would be one slug. Now, that would be the conversion under Earth's gravitational field, I should say. Outside of science and engineering, we tend to not use the slug. Most people have never heard of a slug. Even people that do a lot of measurement have never heard of a slug. You might have heard the phrase, there's a whole slug of those over there, or take a slug off of that bottle, whatever. All they're referring to as a slug is actually a pretty large unit. That's where that term comes from, is saying it's a large amount. In our standard system, we tend to focus on weight. And dealing with standard weight, of course, one of the larger units we deal with is a ton. Somebody tell me, how big is a ton?
2,000 pounds.
2,000 pounds is what we're used to, isn't it? That is actually what is referred to as a short or a net ton. 99.999% of the time when you hear the word ton, that's what they're talking about, is 2,000 pounds. But if there's something called a net or short ton, that implies there's something called a gross or long ton. A gross ton or a long ton is 2,240 pounds. Why is there a difference? Well, it's just like your paycheck. If you work 40 hours in a week at $16 an hour, you've earned 40 times 16 or $16. That is your gross pay. That's the whole amount. But of course, you know you don't get to keep that much. They take out taxes and whatever. You might take out of that $640, you might take about $480, $490 home. That is your net pay. Same kind of thing happens over here with our tons. The ton was originally used for measuring grain. You could not just throw a ton of grain on a scale. It had to be in a container. So the container that held 2,000 pounds of grain weighed around 240 pounds. So the gross ton is with the container. What we're always concerned about, though, is the net amount. We don't care how big the container is you get. You care about the net amount of grain that you got. So the short ton was really what you're worried about, how much grain you had without the container. In this class, there might be a couple problems in the homework that have the gross or long ton in it, but I will never ask you about a long ton or a gross ton on a quiz or a test. It'll always be on a quiz or test. When I say ton, I'll always be talking about 2,000 pounds. But I just wanted you to be aware that there is another ton out there that you may run into at times. Now, there's also something out there called a gross. A gross has nothing to do with weight. A gross is just a numerical amount. It's a dozen. It's 144 items. Now, the gross is another one of those units that had different applications in different fields. So in other fields, there's you can order a gross of this item. It might mean different amounts, but a gross always means a certain specific amount of items, not a weight or mass or anything like that. Okay, so smaller than a ton. I'm just going to use the word ton because for now on, whenever we say ton, we mean the 2,000 pounds. We had the 2,000 pounds. It would have made sense to abbreviate pound PD. However, in the bookkeeping system for buying and selling grain, like we said, that's where pounds and tons were used. PD was used already as the abbreviation for paid. So we didn't want to confuse pounds with paid. That would be very bad. So they used the Latin word for pound, which is libra. So LB is the abbreviation they used for pound. Smaller than a pound, we have ounces. There are 16 ounces in a pound. Now, since they used the Latin word for pound as the abbreviation, libra for LB, they did the same for ounces. The Latin word for ounce is ounza. So they used OZ for the abbreviation for ounce. Smaller than an ounce, there's a dram. There are actually 16 drams in an ounce. A lot of people, when they see the unit a dram, they think it's a metric unit. It sounds a lot like the gram, which we'll talk about in a little bit, but it is different. A dram is standard, and it was one of the original apothecary units. It was like a little thimble size container that they used to measure out medications. You might be prescribed an eighth of a dram or a quarter of a dram of a medication. There were minims that are only used in the medical field. A minim, there were 60 minims in a dram. Actually, I think it's MINIMS. The minims kind of have faded now that the medical field has pretty much totally switched over to the metric system now. And there's also a grain. Now, I don't know why they always went back to pounds for grains, but they do. 1 pound is 7,000 grains. Now, a grain was like a grain, a current little speck of sand or salt or whatever. I believe they used sand because the grains were also used to measure time in your hourglasses. So they literally counted out the grains of sand. Now, eventually they developed a little bit more technology. They used like little tiny containers that they knew would hold approximately a certain number of grains, and that's how they measured grains rather than counting out each individual speck. But grains is the standard for medication for a lot of years in the standard system, to the point where it was so ingrained in the medical fields, grains have actually been absorbed into the metric system for medical purposes. Now, it was absorbed very, very poorly into the metric system, and we'll look at that later on. Some conversions we have. 1 gallon, we should specify, of water is 8 pounds. 1 fluid ounce of water is not quite exactly, but really, really close to 1 ounce. So we do have not terrible conversions from our weights into our capacities, but it's not near as nice as what it is in the metric system, as we'll see in a little bit. Now, something I like to point out, just because you hear a lot about it, you hear all the time on the news, gold has reached, $2,000 an ounce or whatever, or silver's at $100 an ounce. We had mentioned a couple of weeks ago, that King Edward declared his thumb and foot and everything the official measurements of the land. And we had mentioned how that was done by different rulers in different regions around the same time. So those standard units are not standard from one region to another. Well, weight, of course, is the same type of thing. It was declared standard in each different region, and they had different standards. So the pound and the ounce are not worldwide standards. Well, historically, the center for buying and selling precious metals like gold, silver, platinum, and whatever, is the island of Troy off the coast of Greece. So when we buy and sell precious metals, we still use Troy measurement, Troy units. Or Troy weights. In the Troy measuring system, 1 Troy pound is approximately 0.82 US pounds. So the Troy pound is slightly smaller than what we're used to as a pound. However, 1 Troy pound contains only 12 Troy ounces. So even though the Troy pound is slightly smaller than the US pound, a Troy ounce is actually slightly larger than what we're used to for an ounce. So when you hear gold hit $1,900 an ounce, they're not talking about what we think of as an ounce. They're talking about a Troy ounce is what they're talking about. So slightly bigger, not a lot, but just slightly bigger than what we're used to using as our ounce. We'll never be tested on that, but I like to throw that out there because you hear so much about price of gold, price of silver, and all that. If you listen to the financial news at all, I wanted to point out that those are not the same units that we're used to. And it's kind of a nice illustration of what we talked about before of how standard units were not a worldwide standard. They were regional standards. You had different standards from one region to another. Excuse me, made it very difficult to trade between countries using the standard units. Let's talk about metric. In the metric system, they tend to focus on mass because mass did not depend on the force of gravity. It didn't change from one planet to the next or one region of the Earth to the next. So let's talk about metric weight or force first. A unit that if you had chemistry or physics class in high school, you probably heard of a Newton. May have even heard of it in physical science. A Newton is the measurement of weight. Now, a Newton is not as nice and neat as our other units because it depended on the force of gravity. And gravity is not a nice, neat little unit. A Newton is about 9.8 kilograms. Or sorry, 1 kilogram, I should say, is 9.8 newtons. We tend to focus in the metric system on mass. The unit of mass they use is a gram. A gram was defined, we talked about how they planned this out. It is the mass of 1 milliliter water. So remember that 1 milliliter was a cubic centimeter. We fill it up with water. The mass of that is 1 gram. So there's a link between volume and capacity, and now there's a link between our capacity, volume, and our mass. Our links all work together, our units all work together. So our gram was our main unit, abbreviated with just a G. Just like with our other units in the metric system, we have prefixes going smaller. A decigram, a centigram, or a milligram. Of course, milligram being 1,000th of a gram. We skipped 10,000, 100,000 and went to micrograms. Again, if you're in the medical field, that would be mcg rather than μg, just because of the keyboarding on the computer. Going larger, we had decagram, 10 grams. Hectogram was 100 grams. And a kilogram, or 1,000 grams. If you watch any movies about drug trafficking or whatever, you hear the term kilo or key even. That's what they're referring to as a kilogram. And of course, the kilogram was 1,000 grams. Excuse me, they skipped 10,000 and 100,000. They jumped up to a million, which is a megagram. Now, the megagram actually has been adopted. 1 megagram is 1,000,000 grams, but more usefully, it's 1,000 kilograms. Because of the relationship between kilograms and pounds, that has been adapted to be called 1 metric ton. So 1,000,000 grams or 1,000 kilograms is a metric ton. If you listen to that financial news at all, like we were talking about with the gold and silver, you hear about, corn is going for a certain price per metric ton or whatever. That's what they're talking about. When they're talking about any sort of international trade and the price is by tons, they're talking metric tons anymore. Now, our conversions here are the exact same as they were for any other metric unit. If we had 0.47 grams, and I'm converting that into milligrams, from grams to milligrams is 3 spots to the right, so I move my decimal point 3 spots to the right, filling in a 0 for that missing spot. That's 470 milligrams. if we want to look at our conversion between standard and metric here. 1 kilogram is approximately 2.2 pounds. Now it's actually 2.208. Some people use 2.21, some use 2.208. The reason I'm using 2.2 is in the medical field, that's what they've settled on as their conversion. So a 200-pound person, we want to convert that into kilograms. We're going to put pounds on bottom here. Kilograms on top. You may notice, by the way, that I always underline pounds, my LB, when I use that abbreviation, because if I put a 1 in front of it, what is that 1B or is that LB? Putting that line under it just signifies that that is LB. So 1 kilogram is 2.2 pounds. The pounds cancel out. That's going to be 200 divided by 2.2, which gives us 90.91 kilograms. So you can see that approximate deviation there. The 1,000 kilograms, the metric ton, let's take a peek at that for a second here. If I convert that into pounds, 1 kilogram is 2.2 pounds. Well, the kilograms cancel out. 1,000 times 2.2, that's about 2,200 pounds. So the metric ton, as you can see, is actually between our standard net ton and gross ton, but it's a little bit bigger than the net ton, which is what we're trading in, is net tons. The metric ton is slightly bigger than our standard ton, but it's close enough. 2,200 pounds to 2,000 pounds is a 10% difference. It's close enough that facilitates that international trade. Now, I'd mentioned the unit grains, where we said 1 pound was 7,000 grains. Well, the grains, by the way, any of you that are into shooting and guns, you look at your 145 grain bullets or 120 grain bullets, that's where they come from as well, as that's measured out in those grains. It was so entrenched, and you won't be tested on this part. I'm just showing it. Any of you that might have EMT training or paramedic training, you would have seen some of this to show you how it links together. So 7,000 grains is a pound. Abbreviation for grains, so I'm going to put that in there. So 1 pound, or 7,000 grains, is 2.2 pounds. So 1 kilogram I just blacked out on how I want to do my conversion here. So we're going to divide this by 2.2 to turn it into how many grains are in a kilogram. I should say times 2.2. You get how many grains are in a kilogram. So it's 1,540 grains in a kilogram. 15,000, 7,000 times 2.2 is 15,400. Okay, let me try that again. I'm not getting my buttons to work. There we go, 15,400 grains in 1 kilogram. So if we shift that decimal point over to make that grams, there's actually 15.4 grains in 1 gram. By the way, the medical students I work with, they look at GR and they confuse it for grams all the time. GR is the abbreviation for grains. Be very careful. If you see GR, it is not grams, it's grains. Well, that's great. 15.4 grams is a grain. If we go to our milligrams, if I divide 1,000 divided by 15.4, we get 64.94 milligrams equals 1 grain. Now, they do not like ugly conversions like that in the metric system, so what they've done in most medical applications, they've adopted that 15 grains is 1 gram. And I don't know why they didn't use 65 milligrams, but in most cases they've rounded it down to 60 milligrams equals 1 grain. To me, that's very sloppy rounding, but these are the exact conversions. These are the conversions that are most typically used in the medical sciences. So just be aware of those. If you do any first responder or EMT training, you're going to see some very sloppy conversions there as they absorb the grain into the metric system. Now, normally I would give you guys some homework here and let you work, but because of the 2-hour class today, I'd like to just keep going. Does anybody have any opposition to just working through our break and just getting done early at the end? Okay, so if you need to get up and use the restroom, please feel free whenever you need to. Our next section we want to talk about is compound units. The way I usually lead that off is I just throw a challenge out there. If I tell you I can throw a baseball at a rate of 90 feet per second, would you believe me? 90 feet per second. If you're looking at a baseball field, you think of first base is 90 feet away from home plate. That means I could take that ball, I could throw it to home plate and get there in 1 second. Well, the question is that fast? We don't know because we're not used to seeing speeds as 90 feet per second. We're used to seeing them in miles per hour. So in order to decide if you believe me on that, we have to change feet per second into miles per hour. To do that, we have to look at 90 feet per second and realize that is 90 feet per 1 second. Whenever we have a divided unit like that, feet per second, miles per hour, miles per gallon, it's actually two numbers being compared. It's just the second number is 1 and whatever that bottom unit is. So 90 feet per second is 90 feet per 1 second. Now here we have to convert the feet into miles and the seconds into hours. So it's going to require a couple of conversions. Let's do the feet first. I'll put feet on bottom since they're on top so that they will cancel out. And we know that 5,280 feet is equal to a mile. So now the feet have canceled out and we have miles per second. Well, we need to get rid of the seconds. Well, since the seconds are on bottom, we're going to put seconds on top here so that they'll cancel out. We don't necessarily have a direct conversion from seconds to hours, so I'm going to do it from seconds to minute. We know 1 second is 60 minutes, or 1 minute is 60 seconds, I should say. But we don't want minutes either, so I'm going to get rid of those by putting them on top. Since they're on bottom, they will cancel out. We know that 1 hour is 60 minutes. Now we have miles per hour. That's what we were hoping for. So on top here, we've got 90 times 1 times 60 times 60, which is, what's that, 324,000, I believe. That's miles. On bottom, we've got 1 times 5280 times 1 hour. That's 5,280 hours. And now we're just going to divide that out. 324,000 divided by 5,280, I believe is like 61.3. 61.36. That'll be miles per hour. So notice to get it back to a single number with that divided unit, that rate unit, we just divide by the number with that bottom unit, and it gets us down to that single number. So 90 feet per second is only 61.36 miles per hour. I'd have to do some stretching first, but I could probably still throw that fast. So anyway, the purpose here is to look at those dual units and deal with those conversions. We might have something like, let's look at a weight of a roof distribution. The standard roof weight is 60 pounds per square foot. Well, let's figure out what is that in ounces per square inch. Well, let's set this up. So 60 pounds per square foot is 60 pounds over 1 square foot. We need to convert pounds to ounces. So let's do that first. I'm going to put pounds on bottom, going to ounces on top. 1 pound is 12 ounces. So the pounds are going to cross out. We now have ounces per square foot. Oops, 1 pound is not 12 ounces. I'm thinking troy units. 1 pound is 16 ounces. Thank you. Next, we have to get rid of the square feet. Now, it's on bottom, so to get rid of it, I have to put it on top. We're going to square inches. 1 pound is 144 square inches. So the square feet have canceled out. So now we're going to do the top. We're going to multiply 60 times 16 ounces, 960 ounces, over 1 times 144 square inches is 144 square inches. And again, to reduce that down, I'm just going to divide by that bottom number, the 144. The 960 divided by 144 is 6.67 ounces per square inch. We might have things that are measured out as 0.32 pounds per cubic inch. And let's figure out, well, what is that in pounds per cubic foot? So once again, we take our 0.32 pounds per cubic inch, right? It is 0.32 pounds over 1 cubic inch. Now in this case, the pounds are going to stay the same. We're not changing the pounds. It's the cubic inches that are going to become cubic feet. So we don't need to change the pounds at all. Those are going to stay. We need to get rid of the cubic inches. Since they're on bottom, we're going to put them on top so they cancel out. The cubic feet's what we're changing it to. 1 cubic foot is 1,728 cubic ounces, or cubic inches. So the cubic inches cancel out. On top there we have 0.32 times 1728 gives us 552.96. Is pounds. On bottom we got 1 times 1 is 1 cubic foot is just 1 cubic foot. Well, it's already a 1 on bottom, so there's nothing to divide out there. So it's 552.96 pounds per cubic foot. By the way, most of your woods range between 40 and 60 pounds per cubic foot. That's a pretty dense material there at 550 pounds per cubic foot. We might have let's say something is, let's look at silver. Let's say that silver is listed as $72 per ounce. If we want to list that as, what is that in dollars per pound? A little bit awkward the way the units are written because the dollar symbol is in front of the number, but it's the same thing. It's still a rate. So we're going to write this as $72 per 1 ounce. And again, we're keeping the dollars, but we have to get rid of the ounce. So we're going to put, since ounce is on bottom, we put it on top so it'll cancel out. Pounds on bottom. So 1 pound is 16 ounces. Our ounces cancel out. So that's 72 times 16 is $1,152 on top. On bottom, 1 times 1 pound is just 1 pound. Again, the bottom is already a number of ones. There's nothing to divide out. So that's $1,152 per pound. So $72 an ounce is $1,152 per pound. Well, what if we have a pump that is rated at 4,000 gallons per hour? Is that a good pump? Well, most pumps are rated in CFM. CFM is actually cubic feet per minute. They just use CFM because it's a little bit neater to write out and easier to abbreviate. So let's convert our 4,000 gallons per hour into cubic feet per minute. That's 4,000 gallons per 1 hour. We have to change the gallons into cubic feet. So let's do that first. We're going to put gallons on bottom, cubic feet on top. We look up our relationship between cubic feet and gallons. We find 1 cubic foot is about 7.5 gallons or 7.48 gallons, depending on where you look it up. So the gallons are canceled out. We're now in cubic feet per hour. Well, we're going to get rid of the hours. Hours are on bottom, so we're going to put them on top so they cancel. We're changing them to minutes. 1 hour is 60 minutes. So the hours cancel out. On top here, we have 4,000 times 1 cubic foot times 1. That's 4,000 cubic feet. On bottom, we have 1 times 7.5 times 60 minutes. 450 minutes. So 4,000. I'm going to double check my 7.5 times 60 just because it's early. It is 450. So let's do 4,000 divided by the 450 is going to give us 8.89 cubic feet per minute, or CFM. A good pump is usually between 8 and 12 cubic feet per minute. So that's right on the bottom edge of our average size pump. So not a terrible pump. We might have things that are listed as, let me see what I want here. Let's say we've got a feed rate that is going at 4.2 ounces. We want to put that in pounds per hour. So we'll do our 4.2 ounces per 1 minute. We want to get rid of ounces, so we're going to put them on bottom. So pounds on top, 1 pound is 16 ounces. The ounces have canceled out. Getting rid of minutes. Minutes are on bottom. We're going to put them on top to cancel out. We have 1 hour, 60 minutes. The minutes have canceled out. So on 4.2 times 1 pound times 60, going to give us 252, yep. 252 pounds. On bottom, we've got 1 times 16 times 1 hour. That's 16 hours. So we divide by the 16, giving us 15.75 pounds per hour. What we've done here is called dimensional analysis. basically I've used the units, the position of the units, to figure out my conversion factors. Ounces were on top, so I put ounces on bottom. That told me where the numbers had to go in that conversion factor. Minutes were on bottom, so I put minutes on top. That told me where the numbers had to go in that conversion factor. Dimensional analysis and those unit fractions that we called the equal 1, 60 minutes and 1 hour have the same values. That really is equal to 1, are very important in measurement conversions. But it's actually important in pretty much all calculations we do. We can have, let's say we have 8 feet of a material that has a density of 48.5 pounds per cubic foot. Well, we can multiply these together here. 8 cubic feet times 48.5 pounds per 1 cubic foot. We see that the cubic feet cancel out, and what we get is 8 times 48.5 is 388 pounds. On bottom is just 1 times 1 is 1. You'll see the cubic feet have canceled out. So we get 388 pounds. Any rate, and by rate I mean the units that are actually 2 units that are divided, can be used as a conversion factor. This is basically saying that 485 or 48.5 pounds is equivalent to 1 cubic foot. So we could use that as a conversion factor to convert cubic feet into pounds. Just like if you get paid $18 per hour, that is saying that 1 hour is equivalent to $18. Or $18 is equivalent to 1 hour, either way you want to put it. So if you want to know how much you're going to get paid for 32 hours, you can use that as a conversion factor. Hours are on top here, so we're going to put hours on bottom. 1 hour is $18. Hours cancel out. 32 times 18 is $576. Going the other direction, if you know that you need, let's see, you know that you need $792, and you want to know how many hours of work that's going to be. Well, you do $792 over 1. Now the dollars have to go on bottom, so it'll be $18 per 1 hour. And now the dollars cancel out. You have the 792 times 1 hour is 792 hours. On bottom, 1 times 18 is 18. So 792 divided by 18 is going to give us 44. That's 44 hours. So when we're working with these rates, if you're trying to decide, well, do I multiply? Do I divide? And what do? Up here, you multiplied by the rate. Down here, you actually divided by the rate to get where you wanted to go. You can use those units to tell you what needs to be done to make that conversion. You might have a car that is traveling at 80 miles per hour, and it is consuming fuel at a rate of, let's say it is 3 gallons per hour. And I want to know, what is this in miles per gallon? Well, here we have 80 miles per 1 hour. That's what we're starting out with right there. We want miles per gallon. So the miles is going to stay. It's the hours that we have to get rid of. This provides us with that equivalency. We're going to put hours on top, gallons on bottom, and it is 3 gallons per hour. The hours cancel out. 80 miles times 1 is 80 miles. On bottom, 1 times 3 gallons is 3 gallons. We divide that out. 80 divided by 3, 26.67 miles per gallon. So even though that's not a conversion we do very often, so that we don't know whether we're multiplying or dividing or whatever, the units tell us what needs to be done to make that conversion. Now, if we're using metric units, it can be a little trickier. So if we have something that is 280 grams per square centimeter, I want to figure out what is that in kilograms per square meter. Well, we don't have all those like equivalencies in the metric system that we do in the standard system. We just converted by moving decimal points. Well, we can still do that here. We don't need to use those conversion factors in the dimensional analysis. Notice I'm not multiplying by a conversion factor, I'm just putting equals. Let's just convert each unit separately. Let's convert grams to kilograms. On my chart, I had grams in the middle, and it was decagrams, hectograms, kilograms. To get from grams to kilograms was 3 spots to the left. So let's move our decimal point 3 spots to the left. That is 0.28 kilograms. Well, then we had centimeters squared going to meters squared here. So on our chart, we had meters, decimeters, centimeters. To get from centimeters to meters is 2 spots to the left, but this is centimeters squared and meters squared. So every spot on the chart is 2 decimal places. So 2 spots on the chart, 2 times 2 is 4 decimal places. So we're starting here, we got to go 1, 2, add a 0, 3, add another 0, 4. There's 0.0001 meters squared. And now we divide it out. 0.28 divided by 0.0001 is 2,800 kilograms per meter squared. Where it can be a little bit confusing in the metric system is when we have some standard units mixed with it. The one unit that has not been metricized is time. So if we have something that is moving at a rate of, let's say it's moving at 20 meters per second. I want to know what is that in kilometers per hour. So we have 20 meters over 1 second. Here I do have to use a conversion factor to turn my seconds into hours. Seconds, we'll go seconds to minutes. 1 minute is 60 seconds. That cancels out the seconds. We're in minutes. Go minutes to hours. 1 hour is 60 minutes. That cancels out the minutes. So now we'll multiply this out to do that, complete that conversion. 20 meters times 60 is 36. That's 72,000 meters over 1 hour. So now we're at 72,000 meters per hour. We still need to convert the meters to kilometers, so let's do that right now. Notice again, I'm not using a conversion factor, I'm just moving the decimal point. 72,000 meters from meters to kilometers is 3 spots to the left. That is 72 kilometers. The 1 hour doesn't change. So again, we divide that out. That is just 72 kilometers per hour. So sometimes you have to do a combination of using that dimensional analysis if there's standard units of time with it, and then just the decimal point moving for our metric units. We mentioned that there's a couple of things that are not metricized. Time is one of them. One of the other things that's a little sloppy is temperature. If we look at our temperatures, we base them off of water, the temperature at which water freezes, thaws, however you want to look at it, and the temperature at which water boils. Of course, our standard system, we're working in degrees Fahrenheit. In degrees Fahrenheit, at what temperature does water freeze?
32 degrees.
32 degrees Fahrenheit. Very good. At what temperature does water boil? This is one, in recent years, a lot of people don't know anymore. It used to be something we had to memorize in elementary school. 212 degrees Fahrenheit is where water boils. In degrees Celsius, which is the metric temperature, what temperature does water freeze?
0.
0 degrees Celsius. What temperature does it boil? 100. Perfect. There's 100 degrees between freezing and boiling. So the metric system sometimes is referred to as the centigrade system. Centi meaning 100, grade meaning divisions. There's 100 divisions or 100 degrees between freezing and boiling there. So you'll notice, let's go off of that. There's 100 degrees here between freezing and boiling for the Celsius system. If we subtract here, there's actually 180 degrees between freezing and boiling in the Fahrenheit system, standard system. So a degree Fahrenheit is smaller than a degree Celsius. It takes more of them to get from freezing to boiling. The tough part about this conversion is the 0 points are not the same. Every other measurement we did, 0 was 0. 0 meters equals 0 feet. 0 pounds equals 0 kilograms. 0 was 0. 0 liters was 0 gallons. Here, it's not. 0 degrees Fahrenheit is not 0 degrees Celsius. We do not have that common 0 point. So we can't just use a conversion factor. We actually have to use a formula. If we are going from degrees Fahrenheit into degrees Celsius, we take our Fahrenheit temperature, we subtract 32, and we multiply by 5/9. Where did the 5/9 come from? That's 100 over 180. Remember, the number of degrees between freezing and boiling, that reduces to 5/9. That'll give us our temperature in degrees Celsius. So let's say human body temperature, 98.6 degrees Fahrenheit. Let's put that in and convert it to degrees Celsius. So once we've plugged it in, it's just an order of operations problem here. 98.6 minus 32 is 66.6. 5/9 times 66.6 is 37 degrees. So that would be 37 degrees Celsius is human body temperature. If I want to go the other direction, if I want to take degrees Celsius and convert it in degrees Fahrenheit, I just reverse it. Here we subtracted 32 and then multiplied by 5/9. Over here, we're going to add, we're going to reverse that. We're going to divide by the 5/9 or multiply by 9/5. And then we're going to add the 32 in the backwards order. So let's say that you're driving into work or to school, whatever, and you hear the radio announcer says it's going to be 20 degrees Celsius today. Well, is that a nice day? Well, let's go over here and we'll plug 20 in for C. 9/5 times 20, well, that is 36. 36 plus 32 is 68. That's 68 degrees Fahrenheit. I would take that day any day of the year. So the conversions for temperature, we have to use those formulas. If you don't have them down, I'll go back here so you can get them down. Oh, come on now. So you can get those formulas down in your notes. They are the only way we can convert from one temperature to another is using those formulas. Or some sort of a slide rule. Okay, so with that, we'll give you the homework time here for both hours. Don't forget there is that quiz 10-11 sitting out there that from, I believe that was Tuesday, that it was, I pushed it back so it was due today at noon. So for homework out of the big book, you have page 304, exercise 7-15. Page 305. Oops, sorry, that was, I got the wrong number there. Page 304, that's exercise 8-11. Page 305, it's exercise 8-12. Then we jump up for the metric, page 327. That's exercise 9-13. And page 328, exercise 9-14. Then in that packet that we have, that you got a couple weeks ago, that's that Clayton High School packet. In that packet, page 91 through 93, that is these dual unit conversions or rate conversions. Very important that you do some of those. Those are really a big skill to have, being able to convert those rates. And there are also some in the book. Page 307, exercise 7-12. Oops, sorry, 8-13, A and B. (308), exercise 8-14. So I know that's a lot of homework, but it was a 2-hour class today. We have 35 minutes left here. You guys, that's a homework for both hours. So you guys are welcome to use that time to work on homework. I will be here if you have any questions. Otherwise, if you want to